Hey, this is Flickering, and today we have another exotic item. This is a Royal Exclusiv Model 230 controller for the Royal Exclusiv skimmer. Nice big box. I don't get to work on this a whole lot, primarily because um, mostly people are not aware that these are actually fixable. But it came in with the problem that it's not working. Obviously, when I request the controller mailed in, I don't ask for the pump to be mailed in, which limits the what I can test with or what I can fix. But nonetheless, let's open it up for a chance that we can spot a component that doesn't require a repair. So let's take it apart. All right, looks like it has some type of warranty seal or something along those lines on this one um, screw. Okay, let's see. Oh, nice and big. Well, before we continue any further, let's plug it in and see what we get. Okay. No light, no power, nothing on the screen. I bet you that the buttons are not going to work either. So clearly there is a problem. But since we're in the diagnostic stage, I think it makes a lot of sense to just test how far the power goes in this and where does it stop. There's a voltage regulator. This is definitely low voltage, or should be low voltage anyway. Let's test that. Not a whole lot here. Not a whole lot here at all. Okay, time to unplug it and start looking around the board. Alright, so I took the main board completely out of the box so that I can work on it properly. So let's go over the structure of this controller. The fact that we have absolutely no lights, no signs of life when we plug it in, tells me that it does not even generate power to run the controller, the main microcontroller here. So that means that the power supply is dead. Now, the input into this controller is AC. This is where the AC plug goes into. So obviously things don't work off of AC. It's a DC pump. It's a DC controller. There has to be a conversion happening between the AC and lower DC voltage, but we don't see a typical power supply anywhere on here. So let's take a closer look at what we have. All right, let's focus on, again, this is my first time looking at this controller, so I'm going to be guessing along with you guys as well. What I see here is, I see huge capacitors, and those are, by the way, really nice capacitors. Those are nice quality Japanese capacitors, as they should be. Hopefully you can see from here. It's the Nichicon capacitors. They're not bulged, at least I don't think that they're damaged. And then we have, again, this big, huge MOSFET here, and something else that looks like kind of a MOSFET, but this thing is huge. You can also see that there is discoloration around everything here. So that definitely had some, heat dissipation going on. Other than that, where are our power supplies? Looks like the power supplies here are all built in, and there is likely more than one power supply. The way I see this is, so this huge MOSFET, this transistor here, is likely switching power, a lot of current for the DC motor. So somehow, somewhere, it gets connected to the DC plugs down below for the motor. It gets controlled by this circuit over here. So this is some type of a power supply, but that's switching power supply likely for the DC motor itself, and likely not for the controller that's down below. This, however, area here looks like a valid switching DC power supply built in to power the controller, to power looks like there is another one over here, and everything else that's related to talking to this controller, interfacing with it, so that it can manage the pump. Let's do some investigation. The fact that there are huge capacitors here means that we're real close to some pretty substantial power supply. There is a module over here. There is a chip over here. It's an older technology chip. This chip allows an interesting configuration where you can have a smaller scale, less expensive switching power supply without a transformer. You see that there are no transformers on here. That's what threw me off initially looking at this. I see capacitors, I see inductors, but I do not see typical transformer. And if there is no transformer and this chip is present, this is likely, this transformer-less power supply configuration that this chip enables. Essentially takes high voltage DC, high voltage, like 160 volts, something along those lines, and modulates it. It's going through a series of diodes and Zener diodes and smoothing capacitors and inductors and all, and produces lower DC voltage that's fairly stable for consumption of others. There is also this component over here, which is the voltage regulator, and I think that this is likely a 5-volt voltage regulator, so it takes 12 or 16 or whatever volts this thing produces and brings it down to 5, which is then used by the controllers. So let's do some testing. Okay, so first, I am not a huge fan really on working on AC power, because half of my work is under the microscope. I can't see my hands. I don't want to electrocute myself. It's also very easy to short something to AC, between AC and DC, and then this will cause sparks. This will definitely damage components on the board. I do not like working on AC if I can avoid it at all. So typically, if you want to troubleshoot a power supply, instead of providing AC voltage and then being afraid to touch anything here, to turn the board, to do whatever, you can attach your bench power supply to the DC side with much lower voltage. Because at the initial stages of switching power supply, it does not care if it's 120 or it's 30 volts. It just brings it all down as much as it can, down to whatever 12 it needs to do. So instead of using AC, we're going to use DC voltage for this. The bridge rectifier is over on this side of the board. There is not much going on this side of the board other than this. So this bridge rectifier has the typical configuration of, positive. So the AC are the middle pins. The DC is here and here. So this is negative. So this is positive pin. This is negative pin. So we're going to connect my DC power supply to the legs of this bridge, like that. And now we can power it up, and we can test a couple of things here and there on this board. Let's power it up. Okay, so nothing's going on yet. Let's switch over to the multimeter. This probably is a good ground. Okay, 35 volts is what I'm giving as an input into this controller. The way this particular configuration works is that at some point on this coil, on this inductor over here, we're going to get some voltage. So what I did here, when I initially tested this, the voltage out of this inductor was coming out 1.5 volts. There is no way that that's correct. And then what happens is that voltage is supposed to travel across this long trace over here to a lot of components. It goes over here, it goes in this area, it goes over to even this power supply over here. It's all getting 1.5 volts. None of it is designed to work off of 1.5 volts. So we clearly have a problem. So where is the problem that's generating 1.5 volts? Is it this PWM module that's switching too slow and generating less voltage? The problem, or maybe somewhere else in that circuit of the power supply, or perhaps there is a short to ground, or even maybe a partial short to ground that occurs on the output of this power supply by one of its consumers. And maybe that's causing the voltage to go down. So to verify this, I actually had to go ahead and use my X-Acto knife to cut the trace off of this inductor to the rest of the circuitry temporarily. It's okay to cut it in one place, very tiny cut, and then it can be easily restored with just a little bit of solder to put it back in place. So let's take a look now that it's cut, whether or not we're going to have the same 1.5 volt power coming out of the inductor. And we actually have 18.5 volts now coming out of the inductor. I'm also not 100% sure that this is a true short because my lab power supply is showing very little current consumption, because typically if there is a short, something, even if it's a minor short, it's still going to cause a component to heat up. Heating consumes electricity, and therefore you would see even a small consumption on the power supply here. Nothing is being consumed, was being consumed anyway before I cut the trace. So I'm not certain yet if this is a true short or something else. So to do this test, instead of using my multimeter, I'm going to use my load tester. Okay, so before we have anything plugged in, all right, before we apply any load, let's power it up. Okay, so about 17.5 volts. Okay, now let's turn off the load. Let's see what happens when we try to gradually, and immediately goes down to 1 volt. Immediately goes down to 1 volt. And then recovers the moment I release it. Yeah, it does not survive even the smallest load. Okay, I think that's all I needed to see. All right, so this clearly indicates that there is a problem with the power supply. There is no doubt that this power supply is faulty. So what exactly is wrong? It's feasible that the capacitors are bad. It's feasible that the controller is bad. So again, as always, one of the first things that we want to test in the power supply are the capacitors. Now I'm going to test them in the circuit, so the values may not be all that accurate, but let's test this capacitor first. So by the markings, it looks like it's supposed to be a 10 microfarad 100 volt capacitor, and there is nothing. About the same over here, and there is nothing. I'm currently suspecting these 3 capacitors over here, or at least these 2. Okay, so my bet at this point is that hopefully it's just one of these or both of these capacitors that are bad. I found out that this particular capacitor here doesn't seem to hold a whole lot of capacitance in it. So I took it out, tested it, and it turned out to be bad. So now I'm going to remove it and replace it with a good capacitor. All right, I removed this guy. I already removed it previously. I just kept it for polarity so that I remember what is where. Right now this is a pretty hot mess. Needs to be cleaned up. The hope is that this capacitor is all what was failing, because replacing Viper circuit requires having a Viper circuit. It's much easier to find a capacitor than a circuit like this, especially today when there are so many shortages of components. Okay, let's put some flash solder on it. I do not have an SMD capacitor of this size on hand, unfortunately. So I'm going to use a perfect equivalent through-hole capacitor. Okay, and this is the equivalent capacitor that we just installed. All right, now it's time to test. Once again, to save me from the trouble of running high AC voltage, I'm just going to use my lower DC voltage just to see where we are. Okay, now we have it connected. Let's see if we can get anything under load. I already see that my bench power supply is showing some current being used up, which was always at 0 previously. And look at this. We have 16.5 volts coming out. I think we might have fixed it. All right, the controller is partially assembled. Definitely partially, as you can see that there's still missing parts here, but it's ready to be tested. I haven't plugged it in yet. Let's flip the cover back up so we can see if any lights come on. And let's plug it in. And look at this. The screen's coming on. Initialization is okay. Start is okay. Let's see if the menu works. Menu works. The buttons light up. Okay, it looks like we fixed it. So the issue with this controller turned out to be the Viper circuit, which is the DC power conversion circuit that provides power to at least some of the components of the controller, low voltage power anyway. And within that circuit, we had a bad capacitor. This is actually not a bad capacitor in terms of the quality of it. This is a Nichicon, very nice Nichicon capacitor, but they also have shelf life. They also have useful life, and eventually, sooner or later, they fail. So replacing this capacitor fixed the controller. Well, this completes this repair. If you enjoyed this video, please like and subscribe, and I will see you next time.